Awesome. Thanks, Robbie. So I'm Peter Michael Acera. I'm happy to open up SYNT for this year. And we're starting out with some fun with program synthesis and verification, aka I believe this is the Berkeley block, as we'll find out very shortly. I didn't realize that until just now. But we're going to start out with an invited talk by Sarah Chasins about program synthesis for usable programming tools. Go ahead and take it away.
Hi, everybody. I'm going to go ahead and pop up my slides here. Host disabled attendee screen sharing.
Oops.
I'm going to wait a moment until it's enabled.
Should be fixed now. Try again. Sorry.
No. There we go. Now it's happy. All right. Do you see my slides? Yes. Awesome. All right. So hi, everybody. I'm Sarah. I'm going to be talking about a tool that lets non-coders write programs in 5 minutes that your average CS PhD student couldn't write in an hour. I'm going to be talking a little bit about the synthesis techniques that actually enabled that, but mostly I want to talk about what it takes to get to the point where your tool is that usable by your target audience, that easy for them to pick up and actually use to accomplish their tasks. So we'll dive into the design process and some of the lessons that the project taught us about making synthesis work for real users, and especially why sort of traditional programming by example, programming by demonstration isn't always going to be quite enough. So we're going to start with a pop quiz. I want you all to think to yourselves, have you ever had one of these thoughts? I will use program synthesis to make this task easier, to make this task accessible to more programmers, to make this task accessible to non-programmers. I know it can be a little hard to do interactivity over Zoom, but I'm going to ask everyone to click on that little participants section and get ready to press yes or no. So if you've had any of these thoughts before, go ahead and press the yes button. If you have never had any of these thoughts before, go ahead and press the no button. Well, I get to see these votes. Okay, I'm seeing some thumbs up. Okay, yeah. So I think that's about what I expected, right? It makes sense to me that a lot of people have had this idea. This is a pretty common motivation. But I also want to ask ourselves, are we actually succeeding in this? And so this leads us to pop quiz number 2. So do you regularly use a program synthesis tool? And before you answer, no, the one that you're presenting later today in this workshop doesn't count. The one that you are developing doesn't count. Do you use anyone else's program synthesis tools? So here's our thumbs up, thumbs down. I see at least one thumbs up, so that's really exciting, but not a ton, right? And so this also makes sense to me, right? It's unfortunately not caught on quite as much as a lot of us would have hoped. And then sort of the follow-up question is what about your non-coder friends? Are they using any program synthesis tools? And I suspect here the answer is probably no, despite the fact that a lot of us are motivated by putting program synthesis in the hands of more users. And so this is kind of surprising, right? I think a lot of us, when we first start seeing these demonstrations, start seeing these techniques, we're thinking, okay, people are really gonna like these tools. A lot of people are gonna grab them and start using them. And instead, what we often see is that most of these tools aren't really getting a lot of adoption. They aren't really getting used. And this is quite surprising, but basically what it means is that over the years, we've learned a lot about what users don't like, what isn't working for them, what they aren't gonna actually adopt into their daily practice, but not all that much about what they do like. And so this talk is more about what do they like and how can you figure out for your class of target users what they specifically need.
Sorry for interrupt, Sarah, but you do have like the build order on top of your slides, which are covering part of them. I'm sure I'm not the only one seeing this, right?
Yeah.
What do you see on top?
So like there's like something that says build order, no build effects, and it's covering like the right hand side of your presentation.
This is so weird.
And yeah.
Oh, I'm so sorry.
It's fine. Yeah, it's just one. Yeah.
Figure it out.
I think that if you exactly.
What about now?
No, it's perfect. Sorry about that. Yeah.
Sorry, that's so weird that presenter version didn't get rid of that, and that I wasn't seeing it. Apologies for that. Okay. All right, so we're gonna do a quick glossary here. Thank you for pointing that out. A quick glossary here of useful versus usable. And these are gonna be very casual descriptions, but sort of working enough for our talk today. So useful is gonna be all about whether it actually helps the target audience with tasks that they want or need to do. So is it something that they actually care about accomplishing? And then usable, basically there's this spectrum all the way from, you can get the task done, it is possible, it is doable, all the way to we have made it really natural and intuitive and easy for the user. And it's at that high end of the spectrum where we're getting the tools that are truly usable. Okay, so how can we make our tools both usable and useful? I think a lot of it is about building up this bridge between programming languages and human-computer interaction, because HCI has, over the past decades, developed some really great techniques that we can actually use to both assess and ultimately drive the usefulness and usability of our tools. And I'm going to highlight through this talk a couple of them. So in particular, we can do need-finding research to figure out what real users need. We can do formative studies to figure out what is actually going to put those tasks in range for these users. And we're going to dig in on a couple of these, but basically there's all these different kinds of studies that we can run to do this. I'm going to start with a case study. So this is a domain where we've had 2 decades of synthesis tools that never quite met user needs, specifically web automation. So this is an important domain, right? There are a lot of people who already care about getting web data, and we see that it's only continuing to grow. The trend that's most interesting to me is how the breakdown of the people who are interested in web data is actually changing over time. So before, it tended to be people who have the kinds of programming skills that folks in this virtual room have. And then going forward, we're seeing that more and more non-coders are realizing the potential of web data, which makes a lot of sense, right? There are all kinds of things that you can do once you have your hands on it. This is a couple of things that our social science and other domain expert collaborators are doing right now. I'm going to highlight just one. So this is a team from sociology that is basically using real-time Craigslist and apartments.com data in order to figure out basically how should we set the rent thresholds for the housing voucher program in order to help low-income families move to high-opportunity neighborhoods. And so there are all these really interesting problems that you can tackle if you can get your hands on the web data. But when we started out building this tool, we didn't know that, and so we first reached out. So we found an email list of basically a bunch of social scientists from a variety of different fields. We asked, do you need web data? And we expected, you know, we'd get a few answers, maybe here, okay, they need it for this, they need it for that. And instead what we got was sort of a flood of emails, and it was really hard to get anything done for the next 24 hours while we were responding to all of these. But it was also fantastic because it meant that we had this big group of basically social scientists and other domain experts whom we could then reach out to when we needed to run an interview to figure out about their needs, when we wanted to run a user study to evaluate prototypes of our tool, whatever the thing that we had in mind for, you know, what would a user think about XYZ, we had this pool of people we could actually draw on. I'm going to talk about how we actually used that. But one of the things that we learned right off the bat, one of the very earliest insights, is that there is data out there, people do want it, and with the tools that were out there at the time, they aren't able to actually get it on their own. Which makes a lot of sense because web automation programming is actually quite hard. So this was from a user study that we ran where we were figuring out, okay, how long does it take for computer science PhD students, so people who have quite a bit of programming expertise, to actually do these tasks? And you can see that over the course of the hour that we gave them, only 4 out of the 15 were actually able to complete the web automation task we set them with a traditional programming language, a traditional web automation language called Selenium. But we can get them to the point of 100% completing it within 10 minutes if we just give them the right tooling. So let's talk for just a quick moment. We're going to do another quick quiz about why this is such a hard problem. So here the goal is to scrape product price over time. This little snippet here is going to be going through all of the nodes in the web page, looking for the node that has $26.06 in the text. So does anyone want to unmute themselves and say why that is not actually going to work? I'll give you the spoiler, which is that it's not going to work. Any ideas?
Dollar is a variable.
Ooh, that's a great guess. So it is related to the dollars, the $26.06 thing, but it's specifically in this case because the fact that we're actually looking for that particular text, that's not going to work anymore once the number of dollars changes, right? So if the product price changes, all of a sudden that's not going to be the right way to find that node. And so in order to actually get access to this data reliably over the long term, we need to do some reverse engineering of the page structure. We need to figure out, you know, what's going to be stable, what's going to be unstable. We have to have some robust and reliable way of finding this information over time. Okay, and then here is our second snippet. And so here the goal is to scrape the first entry in our Google autocomplete menu. And what we're going to do is we're going to pop our query string into the text box, and then we're going to go to the place where the first autocomplete item should show up. So anyone have any ideas why that's not going to work? Yeah, this one's a little harder, right? I told you web scraping was hard. All right, I'll let the cat out of the bag. So here it's because basically we would have to reverse engineer the JavaScript code that's running on the page, because what's actually happening when the autocomplete menu comes up is that the various keystrokes that you've put in have triggered a JavaScript handler that's running on the page, and that has actually gone ahead and loaded the autocomplete menu. And so if all we do is pop that query string into the text box, that actually wasn't anything that triggered the JavaScript handler, and so it doesn't actually run. And so we really need to trigger all those low-level JavaScript handlers in order to get the page to do the thing we wanted it to do. Okay, one last quick quiz. So here we're trying to grab a product variant and put it into our Amazon cart. So first we're going to click on product variant number 2 there, and then we're going to go ahead and click on the add to cart button. Any thoughts on why this little snippet isn't going to work? Yeah, it looks like it should work, right? Yeah, so this one's pretty tricky. So basically what's happening here is when you click on that product variant, the first thing that's going to happen is the page is going to get all grayed out, and it's going to communicate visually to the user, oh, we're not ready to advance, right? We're talking to the server, basically. We're waiting for more information to come back. But nothing actually prevents you from clicking that add to cart button. And so if you go ahead and do that before the page has actually come back with the new information, you're going to end up adding the old product variant to your cart. So there's all these different things that we have to do in order to actually write these programs. Now, if you're a program synthesis person and you're looking at this problem from a high level, you might say, it looks like what's happening here is the user is doing some actions, the browser is coming back and giving us some data. Let's just take a look at what actions the user is doing. Let's pop those into an imitation user, and let's actually use that to automate our task. This is our programming by demonstration approach. And in fact, this has been a long-standing dream in the context of web automation, ever since it made sense to talk about recent versions of Netscape Navigator and making sure you work on recent versions of Windows 95. And one of the first things that folks realized was, okay, it looks like there's some logical tables over here on this web page. Let's go ahead and extract those. Another thing people realized was it looks like people are interacting with the pages for the context of testing. It would be really useful if we could sort of record a sequence of interactions and then go ahead and replay it later. But then around 2009, we still hadn't gotten to sort of the kinds of programs that, say, my social science collaborators would need in order to do their tasks. And then the web started getting much more interactive, which started making this process even harder. And at that point, web PBD progress basically stalled. I'm going to talk about how we unstalled progress. We're going to do a quick demo. So anyone have any idea what kind of data we should look at to figure out when computer science researchers peak? What website might you turn to, or other sorts of data? Go ahead and unmute yourself and say something if you have an idea.
Why, ResearchGate, of course.
I love it. Yes. So in this instance, we're going to be looking at Google Scholar in particular, but yeah, same idea, right? Let's go back through all these authors and all of their papers and get some information about them. And so here, what we're going to do, I'm going to just walk you through how this demo is actually going to work before I actually show you the video demo. Basically, the user is going to open the browser extension. They're going to start collecting information about the first row of data that they want. So in this case, it's going to be information about that first author and the first paper by the first author. So here they're collecting information about the first author. They've gone on here and collected information about the first paper by the first author. Now that they've collected all of the info from the first row, they can go ahead and say stop recording. At that point, the tool is actually going to analyze the web pages with which they interacted and say, okay, they interacted with the first author here, maybe they want to interact with all authors. They interacted with the first paper here, maybe they want to interact with all papers. And so then we get this program that you see here on the left. The user can go ahead and run it, and then we start getting our data set built up. So here's how it actually looks in practice. The user opens up the tool, collects information about the first author, first paper by the first author. Now we've got the program being generated. And then over here, they can actually go ahead and run that script. So that's how it actually works. So let's rewind for a moment. If web PBD has been such a long-standing need, why were we in this situation of users not really liking the tools that existed for so long? I'm going to take us through a couple sort of interesting passages of papers that started pointing us to the answer. This is from a beautiful paper by Tessa Lau, and what she was realizing was that when users have done 6 really repetitive demonstrations, it's really frustrating if they then find themselves in the situation of saying, I could just put in this one little tweak. I know exactly how to express it in natural language. I just want to be able to edit it and tweak it to actually do the change that I want it to do. I don't want to give a 7th repetitive demonstration. Other tools were finding that it was really confusing if users had to give sort of one demonstration for this part of the program, one demonstration for this part of the program, multiple different classes of demonstration. And then sort of we have this one sort of big program synthesis success story for end users, which is flash fill. And when they were actually putting it into Excel, one of the things they realized was that if you give users the correct program after one example, then they are happy. And if you do not, then they are not so happy. And so basically we have a couple problems here, right? So both the useful and the usability are a little in question. So we hadn't reached the point of actually giving users the programs that they needed. And so we hadn't reached the point of being useful yet. We also hadn't actually reached the point where people were, happy using the tools. The tools were still frustrating. They were still unpleasant to use. And so we were giving them PBE tools, but they were still tough. And this leads us to formative studies. How can we make this so that the tool will actually be usable by real users? And so let's diagnose what's going wrong in all these snippets. If you paid attention, there was actually kind of one thread running through all of these. So here, these users were frustrated about multiple repetitive demonstrations. These users were confused by needing to give multiple demonstrations for different parts. These users just wanted to be getting the right answer from one example. And so the running thread throughout of this is that you really only get one example. You've got to be able to give them the right thing, or at least something close, after a single demonstration. And so we started asking ourselves, could we do PBD with one demonstration? Now, we're a synthesis team, so of course our first instinct is that no, that's a wild idea, because that's a wildly ambiguous specification. Which it really is, right? So say we collect this information about the first paper by the first author. Does that mean we want the first paper by all the authors? All the papers by all the authors? Do we want all the papers that have more than X citations? All the papers that mention the word learning in the title? Any of those are consistent with the demonstration that we gave. The observation that actually ultimately led our approach is that for these users, drafting programs is really hard. So they have blank page syndrome, basically. They sit in front of a blank editor window and they're really intimidated. And so even for domains where they actually do have some amount of programming training, and a lot of these users do, right? They're getting one semester of Python data analysis, or they're getting one semester of R data analysis. Even for those domains, they're never sitting down and actually starting from scratch, starting from the blank page. Instead, what they're doing is they're grabbing a program that they used in a prior project, or they're grabbing a program that they used in a particular class, and then they're tweaking it until it actually meets their needs for their current project. So drafting programs is hard, but editing programs is easy. And so this was the approach that we ended up ultimately taking. And in fact, this makes sense. This ties into one of those earlier insights that we were talking about, right? So here the users are expressing they actually wanted to be able to directly tweak and edit the programs that they were getting back. And so this points to the fact that we need editable programs. Users need to be able to edit to resolve ambiguities, and they already want to do this. As this points to sort of the two key things that we realized that we would need in order to make these tools usable by real users. So it needs to be a single demonstration, and it needs to produce editable programs. And unfortunately, those had not yet been delivered over the course of the history of web PBD. So let's move away from that sort of traditional programming by demonstration approach of throw a bunch of demonstrations in, pop that into the synthesizer, out comes a program, out comes the output of the program. The user can look at the output. If they like the output, great, they're done. If they don't like the output, they go right back around that loop, giving another demonstration. What we introduced instead was this demonstrate once, revise anytime approach, where the user gives a single demonstration. The synthesis algorithm turns that into a draft program that's close enough and readable enough that the user can directly edit it to get to the exact program that they actually want. So as you can see, this maps exactly to the things that we realized we needed for usability. So single demo, editable programs. I want to talk briefly about why one demonstration really is better, so much better than two demonstrations for our purposes. So we already talked about the fact that it makes users successful and happy. It's also going to dramatically change our demands on us as the synthesizer producers. All of a sudden it's okay if we can't reach every program in the program space, as long as we can get close enough that the user can edit it to the point that they need it. So that's really interesting. That changes the constraints on us. We also suddenly need much less sort of supporting infrastructure. So we don't need the ambiguity detection layer. We don't need the interface that's going to solicit the disambiguating demonstrations. It also changes the class of programs that we can tackle. So all of a sudden we can tackle long-running programs or programs that produce really large outputs, because we're not demanding that the user actually read all of the output in order to do their debugging. Instead, it's okay if they're actually looking at the program itself to do their debugging. So we're going to be developing usable drafting tools. We're going to be developing learnable languages. And of course, this maps exactly to the things that we were talking about being necessary for usability, the single demonstration and the editable programs. But of course, these tools are also usable outside of Dora workflows. So these are things that we might want just in general. The Helena project was sort of a long-running project with a lot of different sub-goals, and it ran for a while. We're just going to focus for a moment on two of the key ones that are about usability. So specifically, how do we synthesize complex programs from a single demonstration, and how do we make sure that they're human readable? So we did some mean finding research. I talked earlier about how we got in touch with all of these different social scientists and other domain experts. And this was really, really valuable for basically sitting down with them and figuring out, okay, what is the target data that you actually want to get? And what does that mean for the kinds of programs that our tool needs to be able to produce? And one of the things we realized right off the bat was that they need multi-load data. They're not just coming to page A and saying, give me the data that you see on page A. Instead, they want data that they're accessing via clicks, via, they're going to the next button, the more button, they're interacting with forms, they're interacting with widgets, they're typing. They're doing all the same things that you or I would do to get access to data on the web, to be interacting with web pages. And they also want hierarchical data, so that's tree structured output data. It's not just give me the table of authors, it's give me the table of authors, the table of papers, and make sure you're maintaining the connections between them. And unfortunately, up until that point, that really wasn't something that had actually been delivered by prior tools. And so it was really about, first, let's figure out what tasks these folks actually need to accomplish. Do the existing tools meet those needs? If they don't, we need to give them the tool that does. Okay, so that hadn't been accomplished yet. Now, why is it so hard to actually give them a hierarchical data tool? So basically, it's because you end up needing nested loops. And I suspect a lot of the folks in this audience realize why that's scary, right? So if your class of allowable programs is node loops, well, that's like probably still a pretty big space. If it's programs with one loop, well, that's a huge space. With multiple loops, now we're really getting into dangerous territory. And so here we hit a fork in the road. Do we just keep pushing on sort of the traditional smarter, faster synthesizer approach? Or is there some other way? Is there something else we can do here? And basically what we realized is that we can take a look at the class of demonstrations that we allow. So demo number one, we're sort of looking at some papers, we're going on back to the list of authors. That would be a fine way to demonstrate for a human that you're explaining the task to. Demo number two is the demo that I actually gave during the video demonstration. Now, both of these are fine ways to explain to a human user, but one of them is going to be a lot easier for the synthesizer. And so basically, if we allow all possible demonstrations, there's no better search strategy than just search the space of all possible Helena programs until you find one that is producing the data that the user has given you. Wait until you find something that fits. But if we can constrain the user, we can do something much smarter. So basically, there's this class of synthesizer-friendly demonstrations within the class of all possible demonstrations. And for various subclasses, we actually know here's how you would build a synthesizer that turns that into the output programs that we want. And for anything outside of that, we just don't know how to build that synthesizer or compile it. And then over here, we have the user-friendly class, right? If we push too far towards making something synthesizer-friendly, we've seen what happens. We end up making a tool that doesn't work for real users, that's frustrating, that's tough. So we need to find something that's going to be at that intersection, right? We need it to be something that works both for the machine and for the user. And the way we actually did that, the way we landed on a simpler synthesis problem that is still user-friendly is by making a contract with the user. Which basically, this isn't how we would actually describe it to the real users, but basically what we're asking them to do is demonstrate the first iteration of each loop, ordered from outer loop to inner loop. And we were helped with the second one by the fact that the web basically enforces that you traverse from the outer loop to the inner loop. Okay, so this dramatically reduces the synthesis problem. All of a sudden, all we have to do is figure out where do we insert loops in this basically straight line trace and over what tables. So where do the loops go? Let's assume for a moment that we actually know what tables are interesting. That's a big assumption and we'll get back to it. But basically, we can go ahead and label all of the actions that you took according to whether they used any of the table cells. At that point, we can go ahead and add a loop that starts before the first use of any of the table cells and ends after the last use, exactly what you would expect. Let's actually find those tables. So assuming we know about tables is a pretty big assumption. So if you are looking at this web page, do you think that on this web page, get ready with your yes, no button, do you think that there are other rows of data that are logically similar to this data on this same page? You can go ahead and press yes or no. Okay, so I think, yeah, there are probably some other rows of this data on this page. What about for this one? Other rows of apartment data on the same page? Yeah, I think probably not. Most likely not. What about this one? Which of these nodes have more rows of data? Now, this one's weird, right? So like it could go either way because these ones over on the right, it looks like there are other rows of that data down below. But these ones over here on the left where it's highlighting the Gates Foundation, it doesn't look like there's anything more that has that structure. So if we just look for something that has a logical structure of all of those repeated across multiple rows, we're not going to find anything. But if we look at that smaller subset that are just the tweet related data, then we will find something. And so basically that's the same intuition that we're going to use for our table selector synthesis problem. But basically the problem is this: you get the record time web page, you get the set of interacted nodes, and you want to come back with a table that has multiple rows. You don't just want sort of the trivial table that has all the interacted nodes in the first row, but no other nodes. You want to get something that includes as many of those interacted nodes as possible, but it's got to have multiple rows. Okay, so this has dramatically simplified the synthesis program. We have this much more constrained table selector synthesis problem. We don't just have to search the space of all possible Helena programs. We've also simplified the process for the human user relative to when they had to just use traditional web scraping and reverse engineer the web page. Instead, what they have to do here is learn a demonstration contract. And the end result is that users do perceive Helena as much more usable, and perhaps even more importantly, as much more learnable. So you can see the jump here is very large. But they're also much more successful when they're using Helena. So this is again, CS PhD students, so we aren't expecting the social scientists to come in and try to okay, let's.
You can never tell, but I think Sarah might be having internet connection.
One reason. Oops, sorry, what's that?
Oh, your net might have been going just a little bit south there. That's all.
Oh no, are we back? Hopefully?
Yeah, you're good. You're good. You're good.
All right, it was mostly transition, so hopefully everyone is more or less on the same page. Okay, so why learnable languages? So we pop in our demonstration, we get our program, then we need users to actually be able to edit it in order to resolve the ambiguities. So if we're in a DORA workflow, we definitely need learnable languages, but you might want it just in general because of making a synthesis-backed drafting tool, just because that results in users actually trusting the outputs of the synthesizer. So in the past, if we were asking for users to basically do their debugging by looking at outputs, that was okay if it was a small output. They can investigate that. If it's a large output, you really can't expect them to inspect all of that, but you can expect them to inspect the synthesized program, assuming you have actually produced it in a learnable language. And this is especially important for any task where it's long running, where it's a large output, or just it's high stakes and the user really wants to be able to trust what they're getting back from the synthesizer. More web page background. So when you do something that you perceive as a click, or even when you do something that you perceive as typing, what the browser is actually seeing is all of these low-level DOM events. These are really gross, and you don't even really want to show them to a programmer. You certainly don't want to show them to a non-programmer. What we'd really like to show is something like this, like the language that you saw in the video demo earlier. So how do we handle the fact that in order to trigger all of those low-level JavaScript events that I talked about before, we really need this low-level language, while also giving the user something that they can look at? Do we sacrifice robustness? Do we sacrifice readability? What do we do? And of course, the answer is neither. So we can show users this high-level view while still maintaining the low-level information beneath. The way we did this specifically for Helena is we have a reverse compiler from the low-level language back up to the high-level language that we're actually going to show the user. And then the edits that they make at that level, we can go ahead and propagate back down, even though we do still need to maintain all of that low-level information. And we can't just directly compile. And of course, then there are going to be these non-web statements that don't even need to map back down to the DOM events. So this lets us synthesize these huge, but still ultimately editable programs. I want to back up for a sec, just as we start wrapping up. These goals that we were talking about earlier when I gave you the first pop quiz, these goals are important. And they're especially important as we start realizing that more and more non-coders, more and more novice coders are realizing the power of automation, are getting interested in all kinds of interesting and diverse domains in which they want to do programming. And there are all these different ways for them to express their intent, to express what they want their programs to do. If we just started building the tools that could actually consume those, could actually take those as specifications. It's not just about sort of the traditional PBE, the traditional PBD. They are not as constrained in what they can give us as we have long assumed. And so this is really important as we move beyond data. It's not just about data. It's certainly not just about web data. Folks want access to programming languages and tools much more broadly. They have a really strong interest in automation just going forward. And fewer of the people out there in the world writing programs are going to have the kinds of training that we have, the kinds of computer science education that we have. That's going to be only a teeny tiny sliver of the people who are writing programs. And synthesis can help us in this new environment where so many non-programmers are having to write programs, but only if we can make it useful and usable. So how do we do it? We're a PL crowd, right? We need techniques from HCI. And I talked about throughout this some of the ways that we can do it. So before you even start building, you've got to be doing your need finding research, figuring out, is this useful? Is this something that people really need to solve? And then throughout the process of building, we can be doing formative studies. We can be figuring out, okay, is this tool usable? If not, why not? And there are all these different kinds of studies that we can actually do to figure this out. So I'm going to highlight a couple that we used throughout the course of the Helena project, and I'm going to mention a couple more. So we did some interviews, we did some focus groups. All of these were with basically teams of social scientists and other domain experts. We're trying to learn about their programming tasks. We were learning what was hard or easy for them about traditional programming. We were learning what's hard or easy for them about talking about the particular kinds of data they're collecting, about how they would express the problems that they're facing when they're trying to grab that data. We were learning about their mental abstractions. We were learning just what kinds of target data they actually wanted to get. We also did basically we were looking through social science papers, even social science vision papers. We're using that to find target data sets they might want to tackle. We're looking at forums to figure out what kinds of challenges they were facing when they were trying to do this programming in the traditional ways. There are all kinds of different interesting resources, even beyond just talking to people. So I think always the first step should be talking to people. But if you don't have that capability, there are some other options for you as well. Okay, and so then formative studies. Is this usable? How do we figure out how to actually design this tool so that it's going to work for real users? So we were doing interviews, we were doing think aloud studies, we were doing basically user studies even before we had the, oh, looks like my internet connection is unstable. Okay, hopefully it's okay. We were doing user studies even before we had the final tool, basically to figure out, okay, what do we need in order to make sure we're actually meeting these users' needs? And it also gave us a lot of ideas for what to tackle next. What's the next thing they need from us? Do they need us to help them parallelize these scrapers? Do they need us to add a new language construct for XYZ? And so we were talking with people throughout to figure that out. There are a lot of different things you can do with surveys, but I thought one that was particularly interesting. You think of surveys as just asking things like, preferences, like, do you want X or Y, or how do you think about A, right? But so we actually ended up being able to use one to figure out if one of our language constructs that we wanted to introduce was usable, and it let us reach a large group of both coders and non-coders and figure out if they were able to give us all the information they would need in order to actually use our new language constructs. That was really exciting. So you can do some really interesting and creative things. I wanted to highlight just another couple of sort of wild and interesting techniques. So if there is an existing tool in the space and it has logs of how users are actually using it, you can look at places where they're doing things that are really repetitive, or they seem to be struggling, and you can actually use that to realize needs that you might not have realized without those logs. You can figure out, okay, this is a place where people are really stumbling, and maybe we should build a tool that solves that. This is a really interesting class of study, basically a Wizard of Oz study, where you haven't even developed a tool yet. You don't have to have implemented a single line of anything. But if you have a plan, if you have an idea for how you'd like the user interaction to go, you can have a human sitting behind the scenes and doing the things that your synthesizer would be doing in future in order to test out if that's actually going to work for real users. So there are all these really interesting and creative ways that we can figure out if our tools are going to be useful, that we can figure out if they're going to be usable even before we've really finished them. And so I think this is really valuable and really important for us as a field going forward if we want our tools to be adopted by real users and to make a real impact. And with that, I would love to take any questions.
All right. Don't unmute and clap, but you can clap on your own. Great job. That was great. A clap there. Oh yeah, there's a clap thing. Hit the clap button. There you go. Yeah, we do our best, right?
Very
cool. So I'll take a few questions from Slido. Yeah, a bit of time here. So I'm going to just kind of read them off here. First one is from a person named Robbie. In addition to editing the program, might users want to edit the demonstrations as well? Would that be useful to the synthesis engine?
I think that would be really, really cool. Yeah, so in this case, because we are doing just a single demonstration, you can kind of imagine that there's a mapping between the demonstration and the output program, and it's kind of the same to be editing the output program as it is the demonstration. But if you are in a synthesis interaction where you're getting multiple demonstrations or multiple examples, absolutely. Editing sort of the demonstration itself makes a ton of sense, especially because people can really easily paint themselves into a corner. And that's actually one of the other issues that folks often discuss about sort of these multi-demonstration PBD approaches, how easy it is to actually end up getting conflicting demonstrations where, you know, you collapse the program space, there's nothing left.
Yeah, that makes sense. Another question from Anonymous. How much technological sophistication do we assume of the end user in these web scraping scenarios? Does the synthesis problem change if we can assume more of the end user?
Absolutely. Yeah. So one of the reasons that I emphasized that, you know, the need finding was with social scientists and non-technical domain experts is because that should shape when you have picked your audience, that should shape everything you're doing in terms of both the language design and the synthesis design. So your interaction model, the language that you're going to use to express your programs, all of that is going to be just down to what class of users are you trying to reach? What class of users are you trying to help? And so that's why I think it's really important to be doing both your need finding studies and your formative studies, your sort of usability studies with the particular class of users that you in particular are interested in, because it's going to be different for, you know, if you're designing something for CS PhD students versus for, you know, a sociology undergrad who's never taken any programming, that's a very different audience and you're going to want to do different things. And so you really want to be studying the particular audience you're trying to reach.
Good. Let's see. If you have any other questions, post them on Slido. I got one. So I really love the idea of sort of like learnable languages as an artifact for editing and revising. I think that's really good. I wonder, have you, in your work, have you had to navigate the tension between the user expecting to use certain programming constructs or approaches that don't themselves, like, they're not either natural in nature or like something a normal program would do, maybe inefficient, you know, otherwise it's just not the standard thing. Have you had to navigate that difficulty yet? And if so, how?
Definitely. So again, I think in some ways this question ends up coming back to the same answer as the last question. You want to figure out what works for your particular class of users. And so I'll give you just a quick example. So I pushed for a long time on trying to get my users to figure out sort of what we would consider traditional or standard parallelization, because they were starting to use this tool to collect really large data sets. And then they started to want even larger data sets and they wanted them to still run quickly. And I was like, all right, you want parallelization, here's how it's gonna work. And I pushed and pushed and I just could not get them there. I mean, these were folks who maybe a little bit know what parallelization is, and asking them to, you know, do fork join or anything, it's just not reasonable. Now I happened to have a side conversation with one of them one day where I was chatting about data deduplication. And data deduplication is something that they do constantly. It comes extremely naturally to them. And what I realized later after that conversation was that I could steal all the information that they use for data deduplication and actually use it to transparently parallelize their programs. So if I get them to basically use a language construct that they think is just doing deduplication, we can also use that to, under the hood, parallelize. And so we just basically grab that information out for them. So if you're willing to create sort of the language constructs that are customized to your target audience, it does end up that you can get them farther. You can get them making much more complex programs.
Excellent, cool. I think we have time for one more question. 3 more came in, unfortunately, after I prompted, so I apologize for that. Let's take the top one here. Will it help if users can choose the elements the user doesn't want, and technically will it be considered a single demonstration?
If they can pick the elements the user doesn't want. I think I understand the question. So if they gave a bunch of different, they were messing around with a bunch of different elements and the tool shows a program that's going to collect all of them, and then they say, actually, let's knock out these ones. I didn't want those ones. Yeah, so I think this is one of the reasons why it's so important that you can actually edit the program. So all of that can go, like, we can give our one really messy demonstration, and as long as we can go back in and look at the editable program at the end and say, actually toss that, toss that, toss that, here's what I actually want in the output, then we're fine. So it's really all about giving them the flexibility to edit, whether that's via more demonstrations, I mean, that wasn't something that people really liked, or in our case, via giving them the editable program.
Excellent, cool. All right, sorry, I have to leave some questions hanging because we're out of time right now. Feel free to go to Slack and ask those questions. pretty sure Sarah would love to jump in there and have conversation. Let's go ahead and thank Sarah one more time. I'm the only one clapping. It's fine, 100% fine. Oh, there we go. Thank you. Appreciate it. We'll see that. Yes. All right, sweet. Let's go.